Hello and welcome everyone. In this video, we're going to continue with the properties of solutions and specifically focus on now what we call colligative properties. So meaning how do the properties of a solution change once there is a solute dissolved in, or how does the properties of a pure liquid change once there is a solute dissolved in it? And the first property that we'll look at is that of the vapor pressure of that pure liquid. And it's where something about Raoult's law, or someone is called Raoult's law, comes in. So let's imagine a situation, so I'm going to draw it down here, where you have a sealed container and you have a liquid, so some liquid water. And this liquid water will, of course, have a vapor pressure or some vapor associated with it, right? So meaning it has a vapor pressure, and let's call it the vapor pressure of our solvent, because the water is going to act as a solvent for what we're going to do in a moment just now. And to this, we then add a solute. So this can be technically anything, anything that will dissolve in the water. But for now, more importantly, it is a non-volatile solute. So in other words, it's something that will not have its own vapor pressure. So in other words, it's a compound, a solid compound that you dissolve, and it will not have its own contributing vapor pressure to the situation. Typically can be an ionic compound, it could be like a sugar, it could be a protein, something that you dissolve in the water. How does that then affect the vapor pressure of our liquid? So what will happen? What can you expect to happen once this solute has now been dissolved at the bottom here? So there's still liquid water over here. What happens with the vapor pressure? And to maybe just jumping the gun, what happens is the vapor pressure decreases. So how many dots did I have here on the left? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. Yeah. So 5 gas bubbles. So meaning our vapor pressure of our solvent is now going to be less than what it is when it's just a pure liquid. So notice there's a little symbol here that I use, and that indicates that it is for the pure solvent. That is the vapor pressure of the pure solvent, which is larger than that of the solvent with the solute dissolved in it. Okay, so meaning that of the solution. And you might ask for yourself, why is that? And in principle, it has to do with if you now dissolved a solute in your liquid, then you've increased the system. There is more a solute solvent interactions, and that then decreases how many vapor phase molecules you will have. Or maybe that there is some your solvent-solid interaction is not that strong. So in other words, there's no interactions. In other words, eventually there's no change in your vapor pressure. But in principle, because you've introduced a solute, that solute is going to interact with your molecules, your solvent molecules, and hence it kind of, I don't want to use the word pull, but you can imagine it takes more molecules with it and interacts with them, and hence it decreases the vapor pressure in doing so. All right, it pulls more of them into the solution, pulls more of them back into the liquid phase. All right. Now, how do we calculate this effect? So the solvent, so meaning this value here, the vapor pressure of the solvent, is proportional to the mole fraction of what the solvent is. So you then take whatever the mole fraction here is, so mole fraction of the solvent, you can calculate, and you multiply this value with this initial value, and that will then give you the vapor pressure of the solvent after you've added the solute. Okay. So those are the things that you need. You need the mole fraction of your solvent. You need the vapor pressure of the pure liquid. And that then will give you the vapor pressure of the solution. Okay. And this is what we call Raoult's law. So, meaning, I call it the vapor pressure of the solution, but remember, it's still the vapor pressure of the solvent, just over the solution. So that's the more technical term. It's the vapor pressure of the solvent over the solution, but you can think of it as the vapor pressure of the solution. It's because there's no component from your solute. Your solute is non-volatile. All right, but importantly, you remind yourself it is lower than that of the pure solvent, and that is the basics of Raoult's law. Okay, some interesting facts now that we can discuss. So what we call an ideal solution is one that obeys this law precisely. So what is an ideal law? So meaning anything that basically doesn't have too many forces of attraction between the solvent and the solute. So meaning if these interactions are stronger than we expect, then your vapor pressure is going to be lower than what you calculate from Raoult's law. Or if your solvent-solute interactions are weaker than you expect, then your vapor pressure is going to be higher than what you calculated. And that's what I was hinting towards. Like if your solute interacts with your liquid and it strongly interacts, it kind of pulls more of your liquid or your solvent molecules from the vapor phase back into the liquid phase to solivate it. If it does not interact to a lesser extent, then the more of your solvent molecules will remain in the vapor phase, and the closer your solvent vapor phase will remain to the initial solvent vapor pressure. Okay, so that's kind of what when it starts to deviate. But what we will do is we will look at ideal solutions for this course. We don't really look at anything outside of that. This is, of course, Raoult's laws. When you're looking at forces of attraction, that will be an experimental application of it. Okay. A final point that you might want to be interested in is how to calculate the change. So meaning, what is the change in the solvent's vapor pressure? So this change, this delta value here, is what was the final value. So that will always be final minus initial. So that means it's P solvent minus P naught solvent. Okay, so you can use that. And if you look at it a bit more closely, if those things are equal, that means you should be able to calculate for yourself that your standard solvent vapor pressure minus this change in the solvent vapor pressure is equal to the new solvent, or the solvent vapor pressure over the solution, or the vapor pressure of the solution, or whatever you want to call it. All right, and how do you calculate that? Well, that's equal to negative the mole fraction of this solute, and mole fraction of this solute is of course equal to the number of mole of the solute over the total number of mole. And perhaps that's something I can indicate. What is the total number of mole? It's equal to the number of mole of the solute plus the solvent. Okay. The same up top here. Here it says mole fraction of the solvent. So what is mole fraction of the solvent? It must be equal to number of mole of the solvent divided by N solvent plus N solute. Okay. Yeah. And that's basically Raoult's law. Raoult's law says if you dissolve a solute in a pure liquid, the vapor pressure of the pure liquid over the solution will be lower than that of the pure solvent. Okay. And then these are the ways that you can calculate how that changes. So, yeah, now you have that. We also quickly described if the solvent-solute interactions are stronger or weaker than what you expect, how that might affect it. But like I said, that's mainly an experimental application. We won't necessarily look at that too much. All right. Thank you for watching, and I'll see you in the next video.